Here we go. I'm so excited for today. This is going to be a great lesson. So here we go. We have been doing derivatives of power functions. So we have the power rule, makes it really easy, and we can take antiderivatives of that pretty easily as well. We did some application last week. Now we are going to start exponential functions, finding the derivatives of exponential functions. They're a little harder because exponentials, what are exponential functions?
Like 2 to the power of x?
2 to the power of x is an example. It's where the x is in the exponent, and so exponentials have the x in the exponent. So we can't really, in those cases, just use the power rule because the x isn't the base. So the power rule only applies for when we have x in the base to some constant number, even if it's pi. But you have to have the x in the base. For exponentials, if we have the x in the exponent, what do? How do we find the derivative of that? Because we can't just use the power rule. We have briefly played with the idea of the derivative of e to the x several weeks ago. We played with the idea of that, but we definitely did not have the tools to define it and or to find the derivative formula for that. But we do now. Now that we have our derivative definition, we can find the derivative formula for something like e to the x. There's one interesting feature of exponential functions that they all share. What is that interesting feature that all exponential functions share?
I didn't think I was gonna know it. Yeah, I know some.
They're all increasing.
Not always, because
Oh, you can have a
can't
negative
go
x.
lower than the x-axis. It can't go negative, right?
okay, that would be true for all positive bases for sure.
Oh no, because it could be.
You can have a negative x.
Yeah. No, it wouldn't be a negative exponent. It'd be like.
No, yeah, if you had a negative
two
exponent, I mean, if you had a negative exponent, I could do that right now.
It'd be
Then that's when you would have the decreasing.
Yeah.
But yeah, you can't have it go negative. Oh wait, yes you can.
No.
Yeah, because like negative 2 to the third is negative 8.
That's
Right.
goofy.
Right. So, because really what we're doing here is this.
Yeah.
You're taking 2 to the power of x, but then you're just making it negative.
Mm-hmm.
If I had negative 2 to the x, like where even is it? It doesn't show it on here.
It should be a dot, right? Doesn't it, if they graph you, what should that be? What is,
Maybe it's under one of these.
sometimes if you just click, sometimes, like, what should that be? Oh, you don't know what X is. You'd have to plug something in.
Yeah, you'd have to plug some points and whatever, but for now, we really don't care. What is one thing that all of these exponential functions that live above the x-axis, what do they all share in common? Can you think of it?
They have a.
How many can you do?
Ah, I didn't make a new line.
They.
Why would that not work?
What does it do?
I don't know. All right, it's broken. So we'll just do it like this.
You mean to the X?
Why is it just giving me a point?
Because you said squared,
Oh,
you meant to the x.
there we go. Okay. Keep going. They all share in common.
They're never gonna touch the x-axis?
That is true. What else?
Or equal to.
There
If
are other
it's-
things they share in common.
If it's a positive number in the base, that'll go upward, and if it's a negative number, it's gonna
up
go
to the second quadrant.
decreasing to the first quadrant.
Those are not negative numbers.
Oh wait, yeah, they're not.
Third
Less than 1?
Yeah, less than 1. Yeah.
Is that the same for all numbers less than 1?
Okay, how about they all pass through a similar point? What do they all pass through?
Oh no.
And
Ah.
why? And why?
You guys thought way too hard about it. You guys had calculus brains on. You just needed your algebra 2 brains on.
Oh, because if you do anything to the power of 0, it's just equal.
Great, that was exactly what I was gonna ask. Why do they all have that feature? Because anything to the 0 power is 1. That's a definition, right? Okay, so they all pass through the point 0, 1.
Wow.
That's why I
We're
gave you a
dumb.
hint. I knew it. You should have been like, it was an algebra 2 idea.
Yeah, right. You guys had your calculus brains on because you were like, it's increasing, it's decreasing. Those are great observations also, but I was particularly interested in that feature. Okay, because all exponential functions pass through that point. That's a really interesting feature. Like, that makes it really important to us. We should investigate that. I have 2 to the x graphed here. How do we think about the derivative of 2 to the x? Well, because the point 0, 1 is interesting, let's just see what the slope is at that point.
Okay.
One way we can do that is local linearity. Here we go. We're getting straighter and straighter.
Bridge rate.
Okay, looks straight enough to me. Estimate the slope.
Slope. Uh, 4 over 5? Take 1 over 1.
Not 1 over 1, because if it was 1 over 1, it would go through each corner of the box.
4.
4 over 5 isn't bad.
Yeah, I think 0.8.
I mean, you could also look at it this way. If this is 1 unit and then this is 1 unit,
Oh.
then, I don't know, we're going like 0.7?
Yeah. So
Ish.
0.7 or 0.8.
Yeah, I mean, it's about, right? I mean, once you get up here, now kind of less of a straight line if you're going from unit to unit. I don't know. It's not really 0.7, but it's something like 0.7. Okay, let's write that down. So the slope of 2 to the x at 0, 1 is approximately 0.7. All right, let's find the slope of 4 to the x at 0, 1.
I have a feeling it's the same thing.
Why?
Because it's.
Let me see if I can make the color different. There we go.
Oh, no.
Okay, we can still estimate the slope. I'll move it this way and I'll just turn this one off so we're not distracted. I don't know what's the slope. If this is 1 unit, how many units do we get?
It rises 1 and comes 3/4, kind of.
1 3/4.
Yeah, like.
Because for every unit we go this way, this would be 1 unit, 3/4 would be to the 3/4 to the next unit.
Yeah, I'm going, so it goes, it rises, so from 1 to 1.02, it goes up 1 and goes over like 3/4.
Oh, like
Yeah.
3/4 of this.
Yeah.
Okay, well let's just do, we want 1 unit on the x. That's the easiest way to
Okay.
estimate slope. We go 1 unit over on the x, how many y's is it changing by? So 1 unit is changing by 1 and
1.3?
Sure, 1.3, 1.4-ish units on y, okay? So the slope there is about 1.3 or 1.4, okay? So if 2 to the x, so bear with me, if
Ooh.
2 to the x,
Is that double?
yes,
We had a round.
that's reasoning. Yeah, so we could say 1.4 instead, that would be double. Yep, that's a great observation.
So maybe
2.6.
8 would be 2.6, about 2.5.
Maybe, let's do that actually.
Let's try this out here.
Let's try that out.
Let's follow this trend. See where it leads us.
Okay.
Oh! It's looking promising.
Okay, if you go 1 unit on the x to here,
Let's look.
then you're going about 1, 2, and
It's like
2.2-ish
Yeah.
units. 2.2-ish units. I mean, that's pretty close.
Yeah.
So 3 times 2 to the x, right? If 2 to the x is 0.7, 8 to the x we said is about 2.2. What's 0.7 times 3?
2.2, 2.1.
2.21, so that's pretty close, right? So yes, that's a really great observation. That's going to help us later.
Oh.
But what I want to point out is that if we're saying that the slope of 2 to the x is approximately 0.7, less than 1, and if the blue line is approximately 1.3 or 1.4, greater than 1, would you agree that somewhere in between there would have to be a line that has a slope of 1 at that point?
Yeah.
There should be some base between 2 and 4 at that point, 0, 1, that would have a slope of 1, right? The derivative should be 1 there. What is that number? 3, maybe. I mean, we could try it. Oh, oops. I'll go back up. You go over 1 unit, and you're going, oh, just past 1 unit of, so it's like 1.1. So not quite 3, so it's less than 3. So it's between 2 and 3.
2.5.
Okay. Okay, well, here I'm going to take this idea. Okay. If you agree with me that somewhere in between the bases of 2 and 4, there's a number where that slope at 0, 1 is 1, then let's see if we can find the number. That would be a really interesting number. If we could find the derivative of that point for whatever that base is, that would be a really interesting number.
You can name it the Hattie number.
We could name it the Hattie number. Except, here's the thing. The guy who first thought of this and tried to find this out, his name was Leonard Euler. So, and actually I should write that for you because you should recognize his name. Like, you shouldn't already recognize his name, but when you see it typed, you should be able to go, oh, I know that. This is how you spell his name. Leonard Euler. That is pronounced Euler. It's
How is
ridiculous.
pronounced it Euler?
Everyone thinks that when they don't have a teacher to tell them. Yeah. So it is actually said Euler, but Leonard Euler, he was the first guy to try to find that number, and he thought of this first, and so we named that number after him, and we call it E.
Wait, that's what he is?
That is what he is.
No.
Okay? But we don't know whatever that number is yet. We know it's between 2 and 3, right?
Yeah.
It's between 2 and 3. But what is it exactly? We don't know. But we're saying that what our hypothesis right now is that this number, whatever it is, it's going to have a slope of 1 at the point 0, 1. That's our hypothesis, okay? You with me? Okay? So, whatever this base of E is, whatever that number is exactly, it's somewhere between 2 and 3. So, in other words, if we say that f of x equals e to the x, then all we're saying so far, all we know is that f of 0 is going to be f prime of 0 is 1. Right? That's what we're trying, that's our hypothesis, that's what we're defining this as. We're saying somewhere there has to be a base where the slope at 0, 1 is 1, and so then we want to find the derivative of this function, maybe. So we know, we can write that f prime of 0 as 1. But let's use our limit definition of derivative too. We can write f prime of 0 using our difference quotient, so let's do that as well. F prime of 0, now remember what is the difference quotient?
Is it x times x plus h, right? F over.
Right, there's our difference quotient. This is just our definition of the derivative. If we just plug in the information that we're assuming here that we found so far, this will come in handy later, by the way. So we can just plug in our function of e to the x. So we would have limit as h approaches 0 of e to the x plus h minus e to the x over h, which will equal, we're talking about 0 here specifically. So let's plug in 0 for x. F of 0 plus h, no. E of 0 plus e to the 0 plus h minus e to the 0 over h. There we go. And then that can simplify a little bit. And we're saying by definition that this should be 1. Okay? So whatever h is, we're just saying this should make 1. Because at 0, at that point of 0, we should get to 1. That should be the slope at that point. That's what the derivative is telling us, okay? So we're gonna remember this for later, because we're gonna need this, okay? So with all of that, to get us started, let's see if we can't take the derivative of e to the x. Okay, let's see if we can find the derivative function of this. We took the derivative of 1 point at 0, 1, that's 1. So we can take 1 point of this function. But let's see if we can find the formula for this derivative. Maybe it's like something crazy, I don't know, like x times e to the x times, who knows? But let's find out, okay? So f prime of x, okay? We just start the definition, right? H approaches 0, f of x plus h minus f of x divided by h, okay? Now let's plug in what we know. We're trying to find the formula here for the derivative like we've been doing past couple of weeks. So e to the x plus h minus e to the x over h. You should copy it down. Okay, and then now that we're here, what do we do? What could we possibly do? Well, one thing I'm noticing is we have an e to the x in both of the terms on top, right? Think back to your Algebra 2 days. How could I rewrite this term? Is there another way that I could rewrite this
Oh,
term?
it's e to the x times e to the h.
Yes, great. job, Michael. That was 2 years ago for you. So,
Yeah,
good job. Okay, so we're just gonna rewrite using properties of exponents. Maybe that'll help us do something here. Okay, now that I have that factored out, now I could factor out this e to the x and this e to the x from the top of my fraction entirely, right? So as the limit of h is approaching 0 of e to the x, let me write it like this first for you. Yeah. I'm actually going to go straight here, and then you'll just have to tell me if I'm wrong or you don't know why.
What? Oh yeah. You just divide both sides. Yeah.
I'm just factoring this out. I could leave it in the top of the fraction.
It's just written as a
Yeah.
whole number. It's-
Yep, but I'm just taking it out of the top of the fraction because I can. Okay, we're getting somewhere. Now we don't have any x's in our fraction. It's kind of nice. Actually, since that means our limit of h is going to 0, right? So our limit's talking about the h variable. So e to the x here is really just a constant in terms of h.
And we can plug in 0 for h.
We still can't plug in 0 for h because it's in the denominator. We need to get rid of that h in the denominator. But this e to the x is kind of in our way. Let's just get it out of the way. Do you remember the constant rule for limits? If I have a constant inside of my limit, I can just pull it out to the front because it doesn't matter. It doesn't have anything to do with this h variable at this point. So I can just pull it out to the front and I don't have to deal with it anymore. And I'll just have it tag along for the ride until the end. This is thinking back to our limits unit. And we didn't spend like forever and a day talking about this, but we did it in class a few times. So because that e to the x term is just a constant in relation to the h variable, we're just gonna pull that constant out. It doesn't matter what it doesn't matter what x is, because we're looking at the limit of h, not of x. Okay. What do you notice about that term? Yes. How do you know that?
No clue. Well, I don't know. It's just on my paper.
Yes.
Can't
That's
remember
good.
why.
We defined at the start of this, we said somewhere in between 2 and 4, there's a base number, some number, to the x power where the slope will be 1 at 0, right? That was our definition. That's what we were starting with. And now we're trying to see if we can find the derivative of this everywhere else besides 1, right? So we said, okay, well, I know that f prime of 0 is 1 because the slope at 0 is 1. So then we just used our limit definition to make this is equal to 1. So the limit as h approaches 0 of e to the h minus 1 over h is 1.
So you have e to the x.
And look at what we have here.
1.
E to the x times 1. We just substitute what we defined up here in red in the circle. We just substitute that whole term as the limit of h approaches 0 of e to the h minus 1 divided by h is equal to 1. And there it is, limit of h approaching 0 of e to the h minus 1 divided by h. That term is 1. So we just have e to the x equals 1. So we just have e to the x. Thus, if f of x is e to the x, then f prime of x the x. Wow. That's amazing. That's mind-blowing, guys. The fact that this exists, like this is real, the derivative of a function is itself?
What?
Huh?
What?
That's amazing. That's mind-blowing. This exists, this is real. The derivative of e to the x is e to the x. It doesn't change. So the rate of change that e to the x changes is proportional exactly to itself.
So what would it look like?
Great question. Where's e? Functions? Perhaps.
Oh,
There's
it's
natural
a-
log.
I think you have to ABC.
E
Oh, there you
to the x. There you go. It just knows e. There's that black line. Is it between 2 and 4?
Yeah?
Yep. Does it pass through 0, 1? Yep. Does the slope look like it's 1 as we zoom in at this point?
Yeah.
1 unit, 1 unit, 1 unit, 1 unit.
Done.
There you go. We just discovered this. This is amazing. And so, if you, no, now it's going to open Chrome and I don't want to open Chrome. Stop. If you graphed f prime of x, then you would just have e to the x. Again, so it would lay on top of itself.
What?
What? Yeah.
I don't know if you know, but I'm just curious if you know, did he get to it just by trial and error, just getting closer and closer and closer? Like, how did he find
The value of e.
2 point? Yeah.
He used a limit definition of compound interest.
Oh, yes. Okay.
I'm going to share that with these guys on Wednesday.
Oh, sorry.
That's okay.
I was
That's
here on
fine.
Wednesday.
We just don't need it for today.
Okay.
We're defining it differently. So there's 2 definitions for e, which is
So he got
limit
to
of
it
compound
from-
interest, or yeah, that's how
Oh, a limit
that's
of
how he
function.
developed the value. But then we can also define e as the derivative of
Yeah.
0, 1 of slope of 1. That's another way to define e. Okay, so this is amazing. Like the fact that this is real, like the function, its rate of change is itself exactly proportionally. Like that's amazing, you know?
This is at 0, 1.
No, this is the function everywhere.
What?
Yeah. This is the derivative function everywhere on e to the x.
So,
Doesn't matter what x value you put in. If you put in an x value here, 3, you're going to get some number, and that will be the point. But then the rate of change at 3 is going to have a slope of the same y value.
what?
Yeah. It's crazy. It's very cool though. Okay? This is amazing. So, let that sink in. But this is amazing all by itself. But what if I have something like, what if I have something like g of x equals 3e to the x? Is it still so simple? What's the derivative of this?
Found it.
You found the derivative of this already?
No.
You found
I found
e to the 3.
It's weird.
Let's see what happens if we can find the derivative formula for this function. Because e to the x all by itself, I mean, that's amazing by itself, but also it's really simple. It's just itself. But what about this? If I have 3e to the x, is it just as simple? Let's find out. Okay, so what can we do here? Now that we're here, now what?
So do the same thing, so do 3e to x times 3e plus h. Times 3e to h. Hold up. No, you do 3 times, in parentheses,
E to the x.
e to x
E to h.
times e to h. And then you do minus 3 times e to the x.
Okay,
And then
what do they share in common?
bring out 3 and e to x.
Okay, we can bring out the 3 and e to the x. I'm just going to bring out the 3 and show you that here we go. We have this. What does this look like? Look at your notes.
E to the x.
Yeah. We just did this calculation for e to the x. This 3 is independent of the derivative of e to the x. It's just a scalar factor. Because we can factor out that 3 all the way out, then here's there's the derivative of e to the x. I don't have to recalculate it, it's just e to the x. And what was the function we started with?
1.
And there you go. The derivative of 3e to the x is 3e to the x. Okay, what if I have h of x equals 1/5 e to the x?
1/5 e to the x.
Well, I mean, we could show it, right? I can say h prime of 0 would be h approaching 0 of 1/5 e to the x plus h minus e to the x over h.
Which makes sense because the 3 is just a vertical
1/5
shift.
e to the x. What?
Which it makes sense because the 3 would just be a vertical shift, right?
It would be like a stretch or a compress.
Oh, because it's more. Oh, it's not.
But because it's a constant term, though, that's why we can take it out of the limit. And so then we always end up with whatever the constant was. We can just, I don't care about this, get it out of this mess. And then I'm always left with just e to the x. Because here is e to the x. So then now I just have 1/5 e to the x. So now what if I have any constant? C. What do you think?
Just be
C
like
x.
that.
Yeah, doesn't matter.
What
Plug
if
in
you-
whatever favorite number you like for C.
What if you had an addition on the end, like c e to the x plus another?
Well, the derivative, you just lose it.
Yeah,
So
that's a great question.
C e to the x plus 3, the derivative would be c e to the x.
Does it just drop?
I like 7 plus, what do you want to add?
23.
23. Okay, what's the derivative of this term?
7 e to the x. Oh, I guess it would just drop it.
What's the
Because it's
derivative
a-
of a constant term?
Because it's a point, it has no change.
Oh.
Whoa.
This is amazing, guys. This is really, really cool.
This is actually
This is super cool.
Friday
The
was
fact
cool.
that this stuff works
Friday
is
was
crazy.
cooler, but this is kind of cool.
Okay, also open your textbook quickly to page 95. Page 95 has the constant multiple rule for derivatives.
Page what?
Page 95. Go fast, super fast. We're running out of time. We're skipping some problems now because we gotta get to the next thing. And also you guys need to narrate, so. I'm gonna have you narrate in class. But, look at page 95, theorem 3. Constant rule for derivatives. If you are taking the derivative of some function, and you have a constant k attached to it, then it's just the constant times the derivative of that function. In other words, we just discovered that theorem on our own, but we already had it here in page 95. But because we worked it through ourselves, we know that any constant times the derivative of a function is just the constant times the derivative of the function. So the constant just hangs around. Remember when we take the derivative of something to the, with the power rule? It's the same thing. N of x equals x squared, 3x squared. What is the derivative of this?
6x.
Yeah, which is actually 3 times 2x. Because this constant just hangs along for the ride, and then we take the derivative of this function, which is exactly what we just did with e to the x, except that we worked it through. So we already knew this constant rule from when we did the power rule, but now we can apply it to our exponential function of e to the x. Okay? We're gonna time. Okay, I want you to, Jonah, narrate for me what we just did. From red to green to purple.
Okay, so if you start with like an exponential function, you can't use the power rule that you would with the normal like whole number bases, because there's nothing, you can't like do it the same way. So instead, you have to put it into the derivative formula, and then I'm trying to think how to word it.
Sorry.
Oh, so when you put it into the derivative function, e to the x cancels out, and since it's just a whatever like multiplier, you can put it off to the side, and we know that eh minus 1 over h is always equal to 1. So then you can just take that thing we cut out, that multiplier, we just put it in the front of it. And so whatever, like, no matter what your constant is, the slope of e to the x is always going to be equal to 1. And so you can just put your constant back in, and the derivative of any exponential function and its constant is always just going to be itself.
Okay. Michael, do you want to add anything?
So
Or correct anything? Or
there's a guy named Euler, and he was like, "Hey, I wonder what happens when you put the unknown in the exponent instead of the other way around." And so he was throwing some up there, and then he was like, none of these all these cross 0, 1, interesting. But what number is it that at 0, 1 has a slope of 1? So then he named that letter e. That number e. So we know e to the x equals 1, because we defined it, because that's like the whole point of e, is a number that to the power of x equals 1. And then you do all the math in the green, and it shows you that the derivative of e to the x is actually just e to the x. And then you might be thinking, what if there's a constant in front of it, like 3e to the x? So then you can do the same math over again. You're like, it's also 3e to the x. So then you can have this fun little rule that says ce to the x is f of x equals ce to the x, and f prime of x also equals ce to the x. It's kind of hard to say.
Yes.
And then the pink and blue are just examples, and then if there's a constant at the end.
great. Okay. Great. Now e to the x is already awesome as it is, but it's only one example. of a very special base that we handcrafted. What about exponential functions that have any base?
I don't know.
Because remember, 2 to the x had a slope of 0.7-ish at that point. So, okay, so what do we make of that? Are they all the same? Are they all that easy? Maybe. Let's find out. Let's test some functions and see what we get. Let's just start with 2 to the x to get our variance.
Yeah.
So if we say f of x is 2 to the x, then f prime of x will be limit h approaches 0 of x plus h minus f of x over h. You should always write this so that you memorize this definition. Okay. So what did we say our function was? 2 to the x? So 2 to the x plus h minus 2 to the x over h.
So then you can take out the 2.
The 2x.
Yep.
Sure, we could take the 2 to the x out and leave 2 to the h minus 1 over h. And then we could just take this 2x out like all together because it doesn't have anything to do with h anymore. It's completely independent. Huh. So the x term is completely independent of the rest of the derivative. So that means that the derivative of 2 to the x is itself times some proportionality constant, right? That's what we just did with e to the x. It was e to the x, but the proportionality constant was 1. But what's the slope at 2, or I mean 0 of 2 to the x? What's that slope? It was like 0.7 something. So I mean this should be about that, but let's find out what it is. You know, let's take the limit. So we could just plug in some small values for h. Okay, so if I have my calculator, I can just plug in some small values for h. So if I have like 2 to the 0.01, that's pretty small, minus 1, because remember we're tending towards 0, divided by 0.01. Well, that's pretty close to 0.7. Alright, let's go this one. And let's just add like a couple more zeros. So second insert 0, second insert 0. So now I have 2 more zeros. So 0, 0, 1. Okay. Well, it actually is a little bit smaller than this time because 5 is greater than 3. So it's kind of looking like it's tending towards some random number. Like 0.6931. Oh boy. Okay, well let's just record it. What was the number?
2.6931.
0.6931 something. Okay? Okay. This is interesting. Let's just pause here and see what happens if we do a different one. Let's try h of x equals 3 to the x. H prime of x will equal the limit as h approaches 0 of f of x plus h minus f of x all over h. That'll equal the limit as h approaches 0 of 3 to the x plus h minus 3 to the x all over h.
You can go 3 far left.
Pull that 3x all the way out.
3h minus 3x. 3.
Minus,
3x.
we just factored that out.
Oh.
So 1.
Yeah.
Okay, let's plug in some small values of h here. Because the derivative of 3 to the x is itself times some proportionality constant. Second, enter. Now I just need to change the 2 to a 3. Okay. Oh, I mean it's kind of close to 1. 1.0986 something. So this would equal 3 to the x times, nope, 1.0986, so on. Something similar to that. Okay, let's try another one. 8 to the x. Can I skip all these steps and just write this? What do I have here?
8h minus 1 over h.
Good, okay. So then let's plug in some small values, right? Second, enter, scroll all the way over and find small values for 8 to the x. The slope there is like 2.079. So this is about 8x times 2.
Which, can't we simplify out the 8x because it's as h approaches 0, and so we plug in 0 and 8 times 8 to the power of 0 is 1, so the 1 cancels out.
What variable do we plug this 0 into?
Oh, h, my bad.
So it's going to be itself, like the derivative of 8 to the x is itself times some constant that we could calculate. Okay? Interesting. So these derivatives are always itself times some constant value is proportional to itself. But surely these aren't just random numbers, right? They aren't. There's a pattern. You would probably never find the pattern. You would probably never guess it unless I right now ask you to take the natural log of 2 in your calculator. Natural log of 2.
.6931.
0.693. What?
Oh, 0.691.
Is that what it is?
No way.
It's very, yeah, it's very related.
Oh,
What about
2.07.
natural log of 3?
No way.
What about the natural log of 8?
I already did it. It's 2.07.
No way. Are you telling me
That's too
that?
funny, 'cause I was like, those
Mr.
numbers
Hadding,
look
are you a
familiar to me.
witch?
You mean a wizard?
Are you telling
Are
me
you a
that?
wizard?
Are you telling me that these proportionality constants are just a natural log of the base?
No, it's not.
What?
Can't be.
That's so cool.
No.
So g prime of x here is just 8 to the x times the natural log of 8.
What?
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 And this is 3 to the x times the natural log of 3.
No.
And so then this is 2 to the x times the natural log of 2?
No. It's not.
I like those derivatives.
Yes, me too.
It shouldn't be that easy though.
What? Definitely not. This is hundreds of years of math I just showed you. But that's amazing.
Does
So,
it make sense?
Yeah.
We live in a universe that was just randomly
like,
chance.
no, for real, because this, I was just gonna say that, like, this is, no, that's exactly what I was gonna say. God designed this. God designed this from the beginning of time. Like, he created the world, and he was like, I'm gonna design it this way. And then he left it there for us to discover. That's cool. Time has always worked like this. Like, this describes the universe. And God left it there for us to discover. God thinks really cool thoughts. And it's really fun to think those after him. These are the kinds of thoughts that God has. His mind is not simple. He doesn't just think of simple things. God is like, this is clever. And I made this. And that's really cool.
Yes.
And we get to discover that. Like, what a privilege that we can find that. That
was pretty cool. That was cool enough.
Good. I like the end of that speech. Good speech. Yeah.
Wait,
Isn't
so
it amazing?
I feel empowered now. Are you
Good.
Go behind you.
I'm energized.
Don't be
This stuff's cool, guys. This is amazing.
It is kind of amazing. I just got the
Can you
tail
make
end.
some like? Can you make like a Spotify album of like inspirational calculus things for waking up on a dreary Monday in February? And I'm just like, I need some cool calculus. That's a new YouTube. Creighton Hadding's fun calculus morning.
How's that sound like?
We'll be able to
Okay.
For me, that is really couched in Algebra 2 idea. Like, that is just applied in a new and more sophisticated. That's
I'm
really
gonna get sustenance for my boss.
Okay, so
We're gonna get
tomorrow I need you guys to review exponential and log properties from Algebra 2. So I'm to the classroom posted 1 minute ago
Oh, look who's here.
to review Appendix E in your textbook. Appendix E is
That's where I walked in, I was
all the way in the back. And Appendix E has a review of exponential and log properties.
No.
The page number is called A35 for Appendix 35. So read each page in there. There's like 5 pages. Go slow. Make sure you understand every example that they go through, and you're like, oh, I understand what's happening. And then there's some problems to complete that you need to do tomorrow. That's the only time you go. Is review these properties that theoretically you already know. But you need a refresher on these because we're going to use these
Do you have any notebook paper?
as we keep going.
Oh my gosh. Thank you.
Great?
Great.
Please stop that video for me. Gracias.